Good day and welcome to my Campus Guide channel. On this episode, we are going to learn or talk about the PN junctions in basic electronics. We've already talked about a P-type semiconductors, N-type semiconductors, that is under extrinsic semiconductors. If you know you have no idea about semiconductors, that's the intrinsic and extrinsic. Please pause this video. I have a link on this video which will direct you to that video. Please take a look at that one to get a clear understanding on the concept of semiconductors. So to talk about PN junctions and the basic electronics, we've already heard about P-type semiconductors and N-type semiconductors. We said that in the previous lesson that the P-type semiconductors, they are extrinsic type of semiconductors that has a pentavalent impurity. That is, they have 5 electrons on their valence band or the valence orbital, while the N-type, they have a trivalent impurity in them. That is, they have 3 electrons on their valence band or their valence orbitals. Now we want to know what will happen when the P-type semiconductor meets the N-type semiconductors. So let's define what a p-n junction is. When we say a p-n junction, then we are saying whenever a p-type semiconductor material is suitably joined to an n-type semiconductor material, then that contact surface we are having now can be called a p-n junction. That is a point surface for a p-type semiconductor and an n-type semiconductor. So what will happen when these two extrinsic semiconductors come together? And this is the schematic drawing for the semiconductor. Sometimes in our study in basic electronics, we will call it a diode. So on this side, the positive side, we call it the anode, and on the negative side, we have the cathode. And this is the block diagram for it. So this one will be the schematic, and this one will be the block diagram. We already have a clear idea about the P and the N type of semiconductors. We said that the P-type semiconductors, they have holes as their majority carriers. What do I mean by that? I mean the number of holes, or what we used to call protons, are dominated in this type of semiconductors. And in the N-type, we have electrons dominating over there. So whenever they come together, there is a force of attraction in them, because when you come to the P-type, there are holes there. These holes are looking for electrons. They hold a vacancy for electrons, so they need electrons to fill them. And when you come to the N-type semiconductors too, they have enough, or they have in abundant electrons. So these electrons too are looking for holes to fill them. So whenever a P and N-type semiconductor material are first brought together, some of the electrons that is dominating in the N-type will move across to fill the hole, the excess hole in the P-type material. Because those on the other side, that's the holes, are also looking for electrons, they will also cross to the other type of semiconductor, which is the N-type. This movement in the semiconductors are termed as diffusion in electronics. So when we say diffusion, then we are talking about the movement of electrons and hole across a junction. So after these electrons and hole have moved to both sides, or have moved to their opposite semiconductors, there is equilibrium. It gets to a point where the charge on the opposite side of the semiconductors become large enough so they tend to repel or prevent more carriers from entering. What do I mean by that? I mean we are already talking about whenever a P and N type semiconductor come together, the free electrons will move to the P type looking for holes to occupy, while the excess holes in the P type will also cross to the N type looking for electrons to fill them. But due to this movement, that is electronic diffusion or charge diffusion, due to this movement, the charge across this junction become very large. So it get to a point that they will start to repel in a sense that the holes do not need electrons again, and these electrons do not need to fill any holes again. So they become static and there will be no room to contain this excess or this majority carriers on both sides. So there will be equilibrium form. Immediately the equilibrium is formed, you see there were charge carriers on their way to the next or the opposite semiconductors. These semiconductors are not able to join again because the electronic charges occupying those positions are now repelling them or preventing them. So for this reason, there is a potential barrier formed in between these two semiconductors. So we call this barrier the depletion layer. So eventually, after them crossing to the opposite material, a potential barrier will be formed. So this is a diagram to represent that. So free charge carriers can no more rest in position around the potential barrier and therefore become depleted of any free mobile carrier, forming the depletion layer. So from this diagram, you now see the N region, which is the N type, which has electrons to be majority carriers, and the P type, which has holes to be majority carriers. This in the middle here, they were not able to move to the opposite material or to the other semiconductor. For this reason, they are stuck in the middle or they are now found in between the N type and the P type. So they also form their new family over there. So now they are no more N type and they are no more P type. They form a depletion layer in between the P type and the N type material. And immediately there is a depletion layer formed, there is impedance or there is current resistivity. For current to flow through this material, electrons or these majority carriers in the N type, they have to move here. For current to flow, one of these people have to cross to the other end, and now there is a barrier in between. So for this reason, current cannot flow. So there is a need for us to break this depletion layer or this barrier formed between them. For this reason, in our first lesson, we talked about doping. We do doping without requiring any electrical force or requiring any external voltage. But here, we are going to introduce an external voltage or a potential voltage to overcome this layer. If it's not overcome completely, we will help or try our best to reduce or narrow this depletion layer for current to move. So immediately we introduce an external voltage. We call this process in basic electronic biasing. So when we say biasing, is the producing or introducing of an external voltage to overcome the potential barrier or the depletion layer in the p-n junction. The external voltage required to overcome the barrier potential to allow electrons to move freely across a junction is dependent on the type of semiconductor material and the temperature. So for this reason, depending on the material or the semiconductor we are using, we have some amount of voltage to overcome their potential barrier or the depletion layer or zone. So when we take silicon material, that is the most commonly used semiconductor material, you need a range of 0.6 to 0.7 volts to overcome their potential barrier or their depletion zone. So normally we use the 0.7 in our calculations. And when you take germanium, we need a voltage of 0.3 to 0.35 volts. We normally use the 0.35 volts. We need this amount of energy before we can overcome the potential barrier inside these semiconductors for current to flow. So therefore, there is the need for us to apply an external voltage to overcome this barrier potential. So the external voltage, based on how the biasing is done, will either increase or decrease the potential barrier. So our aim of applying this external voltage or our aim of biasing is to increase or to decrease this potential barrier we are now having between the p-n junction. So the first type of biasing we talk of is zero biasing. We have three types we are going to discuss. We have zero biasing, forward biasing, and reverse biasing. Maybe if you're first time hearing these terms, don't worry. At the end of this section, you'll get to understand and know whatever this type of biasing means. So let's talk about zero biasing. Now we are saying these electrical charges are now repairing. The n-type are now repairing holes and the holes are now repairing electrons. So they are in a state of equilibrium. So in zero biasing, we will just short this diode or the p-n junction. What do I mean by we will just short this diode? When it comes to applied electricity or basic electronics, when we talk about shorting a circuit or shorting a diode, then we mean we are just connecting a wire to it. Meaning we assume this wire to have a theoretically zero resistance, so it is not causing any resistance to this diode. So we just short these terminals together, the n-type terminal and the p-type terminal, we short them together. Immediately we do that, some holes that have energy in the p-type will try to move across to the n-type, and those holes that are already in the n-type, that's the minority charge carriers over there, will find this situation very favorable. So they will also try to move back to where they are coming from. They will move back to the opposite direction because these two currents are equal and they are moving in opposite direction. The resultant current will be zero, and this will cause the junction to be in a state of dynamic equilibrium. So for zero biasing, we do not apply any external potential. We just short circuit or we short these two terminals together to get a static or a state of dynamic equilibrium among them. Let's talk about the reverse biasing. For reverse biasing, we are going to introduce a potential voltage, or we are going to introduce a voltage. And for this voltage, we know positive have to be connected to positive. What do I mean by that? In our previous study, we said the n-type semiconductors, they have a negative charge while the p-type has a positive charge. So for reverse biasing in diode, we connect the positive charge to the negative type of the semiconductor. which is having a negative charge, and we will connect the negative charge to the positive terminal of the diode. So because the voltage source is producing positive charge and the charge of these charge carriers over there, they are the opposite of the charge they are producing. They cancel out. What do I mean by that? Whenever we connect this external voltage or we connect this biasing voltage, whenever we connect this voltage to the diode or the PN junction, because it is positive, we are connecting the positive to the N type which has a negative charge. We are saying unlike poles will attract. Those charge carriers over there will try to use that path. The majority carriers or the charges in the N-type region will use the positive path, and the charges in the P-type will use the negative path. So because they are attracting and they have opposite charges, they will cancel out, and the net result is that it will widen the depletion layer because all these charges are moving away from the depletion layer to the voltage source. So for this reason, it widens the depletion layer. That is, it is causing high impedance. It's causing high voltage resistivity. So it is written here that in reverse biasing, the positive voltage is applied to the N-type material and the negative voltage is applied to the P-type material. The positive voltage applied to the N-type attracts the electrons towards the positive electrode and away from the junction, while the hole in the P-type end are also attracted away from the junction towards the negative electrode. The net result is that the depletion layer grows wider due to the lack of electrons and holes and the presence of high impedance path. The result is that a high potential barrier is created, thus preventing current from flowing through the semiconductor material. But when it comes to reverse bias, we are saying all these charges, they will move away from the junction and be attracted to the electrode. But however, we have to take note there is a small leakage of current that will be able to penetrate through the junction or the depletion layer. So we measure this current across that junction in microampere because it is very small in size. Let's talk about the forward bias. So we are saying in reverse bias, we connect the N type to the positive and the P type to the negative electrode of the biasing voltage. But forward biasing, we will not be doing that. For forward biasing, we will connect the negative voltage to the N-type material or to the negative region of the semiconductor, and we will connect the positive voltage to the P-type material. So for this reason, we've already talked about the amount of voltage required to break these potential barriers in the materials we're using. So we are saying if it is a silicon, you will need about 0.7 volts before we can overcome it. But when it is germanium, we need 0.35 volts before we can overcome this potential barrier. The negative voltage repels the electrons towards the junction, giving them the energy to cross over and combine with the holes being repelled in the opposite direction towards the junction by the positive charge. So this will result in the depletion layer becoming very thin and narrow, and which now represent low impedance path, therefore producing a very small potential barrier and allowing high current flow. So because this we are connecting the N-type to the negative electrode and the P-type to the positive electrode. Now the repulsion is happening inside or at the top, that is where the diode is, because now they all have positive charges. They are sponsored by positive electrode to the p type and negative to the n type. So now they tend to attract themselves, so they gain energy to cross. So these majority carriers in the n type will now cross to fill vacancies of the holes, and the holes will cross to come and form. So this will cause a narrowing inside the depletion layer here. So from this diagram, you see the depletion layer here is very small because the charges there are able to cross over for current to flow. So this is forward bias. And let's look at some basic definitions under PN junctions. We talk about the knee voltage or the cutting voltage. When you are talking about knee voltage, then it is the forward voltage at which a diode can start working. So this forward voltage needed for a diode to start conducting is called the knee voltage. We have a breakdown voltage. It is the reverse voltage at which a diode or a PN junction breaks down with sudden rise in reverse current. We also have peak inverse voltage. We say peak inverse voltage. It is the maximum reverse voltage that can be applied to a PN junction without causing damage to the junction. So the maximum reverse voltage a p-n junction can hold without destroying or damaging is called the peak inverse voltage. So this means if a p-n junction or if a diode exceeds its peak inverse voltage, the junction will get destroyed or it becomes very hot. We also have one term called the maximum forward voltage. The maximum forward voltage is the maximum instantaneous forward current that a p-n junction can conduct without damage. So the maximum forward current a p-n junction can conduct without damaging is called the maximum forward voltage. And we have a maximum power rating. It's the maximum power that can be dissipated at the junction without damaging it. The power dissipated across the junction is equal to the product of the junction current and the voltage across the junction. I believe this video was helpful and you've learned something from this. Please, if it's your first time visiting this channel, please hit on the subscribe button and share. Don't forget to leave a comment. Thank you.